for symplectic C star manifolds. And I'll let you continue from here.
Okay, fantastic. Thank you so much for the invitation. So this is going to be joint work with Filip Živanović, a former PhD student of mine who's now at the Simon Center. And so I'll jump right in to the first idea of this talk. So, and let me just do this. Okay. I'm going to look at non-compact symplectic manifolds. So I have here a function h, which is the Hamiltonian, and we're looking at the Hamiltonian flow. And we're doing Hamiltonian Floer cohomology, so that means at the chain level, we're looking at one periodic orbits of the Hamiltonian vector field. So some of these are going to be constant orbits. Those are the critical points of the Hamiltonian. And then as the Hamiltonian grows at infinity, we will start seeing more and more one periodic orbits. So I'm going to assume we're so in many situations, what happens is that this critical locus it gives you a subcomplex of your Floer complex, which calculates Morse cohomology. So that's basically the ordinary cohomology of your manifold. And whereas and this comes with a natural map to called the continuation map to Hamiltonian Floer cohomology. And we're going to be studying this map throughout this talk. So the protagonist of the talk is the kernel of this continuation map. So what this does is it measures the how much of the ordinary cohomology can be represented by Floer chains that involve non-constant orbits. So we have this long exact sequence where we have the annotate here. We have this here we go, and we have the ordinary cohomology, the Morse cohomology here. This is our map. And the quotient at the chain level, the quotient complex, where we quotient out the constant orbits, gives this thing called the positive Hamiltonian Floer cohomology, and we have a long exact sequence. And we're also going to be interested in invariants that don't depend on the choice of Hamiltonian. So we make this Hamiltonian grow more and more at infinity, and we take a direct limit, and this will give rise to the symplectic cohomology. So we have this map C star from ordinary cohomology, symplectic cohomology. Okay, so let me just give just a brief advertisement of the why I got interested in looking at these kernels, and this is because of some work of mine with Mark McLean about the Mackay correspondence. So here we're looking at a situation where we have a resolution of singularities, a Calabi-Yau resolution of singularities of these very nice singularities, Cn modulo finite subgroup of SLN. And the Mackay correspondence, the cohomological Mackay correspondence says that the cohomology of this resolution has a basis that's labeled by conjugacy classes. And this was proved some 25 years ago in algebraic geometry. And our work was to try and reprove this theorem in using Floer theory methods. And in this situation, what happened in the Floer theory case is that the symplectic cohomology vanished. And so we got a presentation of the ordinary cohomology in terms of this positive symplectic cohomology. So basically generated by these non-constant orbits. And these non-constant orbits at the chain level were labeled in a very natural way by the conjugacy classes. This is also, so now we're currently studying the non-isolated case. And these are very natural manifolds to study that come from algebraic geometry. They're typically non-exact symplectic manifolds, very much non-exact at infinity, and they have some very nice properties. Which, for example, here we have the C star action on the base, which lifts to C star action on the resolution, and so a lot of this talk is going to be talking about these C star actions on symplectic manifolds. So this is where this the topic of this talk sort of originated. All right, how do I clear? Let me see, how do I clear all? How does one clear the annotation? Okay, clear all drawings. Okay, great. Okay, and so I'm going to assume now, the second idea is we're going to assume that we're just in a general setup where we have a family of Hamiltonians that are labeled by a parameter A, which we'll just call slope parameter. And this takes values in real numbers except for discrete sets. So typically what happens is that these Floer cohomologies will jump at certain discrete parameters. So those we sort of exclude. And we have these Hamiltonians, their growth increases at infinity, and I'm going to assume that these continuation maps are compatible as we increase the slope parameter. And so what we had before in blue was this continuation map into Floer cohomology. If I now compose with another continuation map that increases the growth of the Hamiltonian at infinity, I get this composed continuation map. And in applications, these continuation maps are compatible in the sense that this diagram commutes. And so what this means is that these kernels that we're looking at, they grow more and more. So we get sorry, 1 second. Pause. Annotation. Scroll. So we get these increasing kernels, and we get a filtration of ordinary cohomology. And I want to show to you now that this increasing filtration of subspaces, these are actually ideals of quantum cohomology. I'm going to assume two more technical things that apply in the classes of examples we look at. So, so first of all, these, as I said, these Floer cohomologies, they typically jump at these certain discrete values that we disallow the slope parameter. So these kernels are stable and they're slightly perturbing this slope parameter. And I'm also going to assume that we have a pair of Pans product, which is additive on slopes. And I'll tell you later situations which all these assumptions hold. But under these assumptions, under this package of assumptions, you get very generally a filtration of quantum cohomology by ideals from these kernels. I can show you actually the proof because it's not too complicated. So imagine that we have a class X which is in one of these kernels, and what we want to do is show that we can multiply by an ordinary cycle, and this new product will still be in the kernel. And remember, I'm allowed to slightly perturb the value of the slope, so I'm actually going to land in the kernel of this continuation map for a slightly larger slope. Okay, and the picture. So the picture to see what's going on is here on the left. We have this diagram. So we have the quantum cycle, and then we have this class X that we know is in the kernel of C star A. Here on top, this horizontal map, we're applying the C star maps. So we have CY, and here CA X, this tensor. And so this is here we're applying we're counting these Floer cylinders. These Floer cylinders that go from the non-constant orbits to these constant orbits. And then this vertical map on the right is this pair of Pans solution here. And this composite, the count of these solutions on cohomology is the same as first doing quantum product, so y times x, and then which is here on the right in the bottom, and then applying the continuation map, which is this horizontal map here. And so because we factor through, because we're assuming that C star CX vanishes, that means that also going along the bottom part of the diagram, we vanish, which means that this quantum product y times x lives in the kernel of this continuation map. And so that's the property that this kernel C star A is an ideal. All right. Okay, so just clear these drawings. Okay, and now I'm going to tell you about which class of manifolds this applies to. So first, the class of examples that many of you are probably familiar with, which is most non-compact symplectic manifolds that we've been studying in symplectic topology, are convex symplectic manifolds. So at infinity, they're very nice. They look like a contact manifold times a radial coordinates. So it's a positive symplectization. At infinity, we typically assume that the symplectic form is exact. It involves this radial coordinate r and the contact one form alpha. And in particular, this means we understand the dynamics quite well at infinity because there's this very nice vector field, the Reb vector field, and we're studying these Reb orbits that live in the slices, which are these copies of this contact manifold. And so there's a nice class of Hamiltonians that you can look at, which are Hamiltonians that are linear in this radial coordinate, so that your Hamiltonian vector field is a multiple of the Reb field. And so as you increase this flow parameter, so let's say your k times this radial coordinate, as you increase the slope parameter, you see longer and longer Reb orbits at infinity. Okay, and the classical example of this is the manifold Cn, where the contact hypersurface is just a sphere, the radial coordinate is just the norm squared, and we're looking at these Hamiltonians that are sort of generic multiples of R, and the genericity ensures we don't have one orbits at infinity. Okay, so this is the sort of classical setup. Now, unfortunately, the manifolds that we've been looking at, so these resolutions of singularities and so on, they're typically not exact at infinity. So they don't fall into this category here. You typically have a non-exact symplectic Floer at infinity. And so we define this new class of manifolds, which we call symplectic C manifolds. So what does this mean? This means we have a non-compact symplectic manifold. We have a C star action acting on the manifold.
Alex?
And yes?
I think your presentation is maybe stuck. We see maybe a previous one.
Your screen sharing is paused. Oh, sorry, I must have pressed the wrong button. No. Sorry. Sorry about the technological things. Okay, excellent. So we have we have our non-compact symplectic manifold. We have a C star action, and now I'm assuming that here at infinity we have a map to this positive symplectization. Now we don't assume anymore that this is a symplectomorphism. So this map here doesn't even need to be a diffeomorphism. And in fact, this target symplectization could have a very, very high dimension compared to your original manifold M. But what we do assume is we assume the following things: that we have the C star action, of which the S1 acts in a Hamiltonian way, and I assume that this map psi is holomorphic with respect to compatible choices of almost complex structures. And so these two assumptions together. And I also assume that the map sends the S1 vector field to the red vector field. So what this means is that I have some control at infinity, because if I pick my Hamiltonians to be for example, a linear multiple of the moment map of the S1 action, so then I have these basically my one orbits of the Hamiltonian are like basically S1 flow but accelerated. This maps down by the psi map to red orbits, so I have an idea of what the generators are, and the condition that this psi is holomorphic means that I also know how the Floer equation of these Floer cylinders, how this maps downstairs. So I have some control of the Floer theory at infinity, which is a crucial thing you need in order to make sense of Hamiltonian Floer cohomology, but also, for example, quantum cohomology in the non-compact case. All right. Sorry, no, I annotate. Okay, now, and I need to clear the annotations. Here we go. All right. Now, a simple example is again Cn, but an interesting, the first sort of non-trivial example is for example an interesting simple example in complex dimension 2 is the A2 resolution. So here we're looking at this quotient singularity C2 mod Z mod 3, where the Z mod 3 is acting by zeta and zeta inverse on the two coordinates, so cube roots of unity. So we have the singularity, and we can embed the singularity via the Veronese map into C3. We blow up the origin, and what happens is that then we get two copies of CP1 intersecting transversely, so two spheres intersecting transversely, living over the singular point 0. And I wanted to show you this example to show you also how this map psi arises in examples. So in this case, one natural choice of psi you might have used is to just simply use these invariant polynomials, because these depend holomorphically on the original coordinate, analytically on the original coordinates. But we also want our map psi to be to preserve the S1 action. So in particular, ideally, it'll just preserve the C star action. And so what we need to do is just take suitable powers of these coordinates. So the square, the square is x to the 6, and then this is y to the 6, and this is x cubed y cubed. So now you see they're all homogeneous of degree 6. The C star action now acts with the same weight, the weight 6. And so now this map is not just analytic, but also C star equivariant. And so we get all these conditions that we need this map psi. And notice also the target is complex three-dimensional rather than two-dimensional. And so this is how these maps psi arise in many examples. So here I've written a list of examples that naturally many of them arise from algebraic geometry. So we have cotangent bundles of CPN, cotangent bundles of flag varieties, negative complex vector bundles. Then the examples I just showed you, which are Calabi-Yau resolutions of quotient singularities. Then there's a large class of examples called conical symplectic resolutions. These are complex symplectic varieties that are studied a lot at the moment in representation theory. Then some classical examples that are called spring resolutions of Floer varieties. Amongst the conical symplectic resolutions is maybe this more familiar class of examples you might have heard of, which are quiver varieties. And then in terms of in the toric geometry, you have essentially non-compact toric varieties. They're sufficiently nice. There's a very large class of toric varieties called semiprojective toric varieties. These all fall into this category. Hypertoric manifolds. This is like a hyperkähler version of toric manifolds. Moduli spaces of Higgs bundles. And then in this recent paper with Filip, we also looked at more generally just a case where you have a C-star covariant projective morphism, and you can do Floer theory. So lots of examples. And so yeah, so let me summarize the main results. So first of all, I'll just repeat once more. So now instead of using this radial coordinate that we're familiar with from convex symplectic manifolds, we replace the radial coordinate just by the moment map of the S1 action. And we're looking at Hamiltonians that are at infinity are a multiple of this moment map, and this multiple is the slope parameter. And so from what we said at the beginning of the talk, we automatically get these kernels of the continuation maps, and they give us a filtration by ideals of quantum cohomology. Now, unfortunately, in Floer theory, it's usually very hard to calculate things, but here a miracle happens, which is that we can actually calculate quite a lot. So what we do is we build a filtration on the Floer chain complexes that gives rise to a Morse-Bott spectral sequence. So let me just say a few words about this. So these orbits that we're getting, so first of all, because we have a time-independent flow, they will arise certainly in S1 families. But in fact, they often arise in quite large families. So they arise so we have these Morse-Bott manifolds of one-periodic orbits. And as we make the Hamiltonian grow, we get more and more of these Morse-Bott manifolds appearing at infinity. The constant orbits that are in the inside of this of our manifold, they just give rise to our ordinary Morse complex. So it calculates ordinary cohomology, or as a ring, it gives us quantum cohomology. So that's this zeroth column of this E1 E1 page of the spectral sequence. And then the higher columns, they're giving us the cohomologies of these Morse-Bott manifolds of one-periodic orbits with some index shifts that are basically these Floer indices, Conley-Zender indices. All right, and this spectral sequence, if we look up to a certain column, up to a certain slope parameter, we get the Floer cohomology for the Hamiltonian for slope k. If we look at all of these columns, or if we do a direct limit, if you like, then we get symplectic cohomology. And here below, I've shown you a picture of what this looks like in the case of the that I mentioned before, the A2 resolution of singularities. So remember, we resolved the origin. We got these two copies of CP1. They give rise to here we have these dots. So the dots represent a copy of our field. We have these two copies of the cohomology of P1. So that's the ordinary cohomology of the manifold. And then as we increase the slope of the Hamiltonian, we start to see orbits. So there's this copy of C converging to one P1, another copy of C converging to this P1. What happens here is that when the Hamiltonian is sufficiently large, we get a periodic orbit of the S1 flow with period 1/3. So these are the periods, and so here we're slicing C by a hypersurface. So we're getting a copy of S1 and another copy of S1, and that gives rise to these cohomology of S1 with grading shifted down by these Conley-Zender indices. And then for period 2/3, we get again two copies of the cohomology of S1. And then for period 1, that means we're actually the Hamiltonian flow is exactly the S1 action. So we get a whole hypersurface worth, a whole hypersurface worth of orbits, and so it's a length space. But since I'm using coefficients and characteristics 0, it's basically the same as the cohomology of a three-dimensional sphere. So that's the cohomology here, again shifted by indices. So you see, you get these various columns that are the cohomologies of these Morse-Bott manifolds of one orbits, in this particular case, this is a Calabi-Yau case, we show the symplectic cohomology vanishes. So we know that the spectral sequence, after enough pages, everything has to, so the differential eventually kills everything. So on this E1 page, we sort of abusively also draw some arrows that actually belong to later pages. But we basically know that everything has to cancel in this spectral sequence, and so a posteriori, without having to calculate any Floer solutions, we can often tell quite a lot about how things are being how things cancel via this Floer differential. So let me just erase this, and okay. So so what's the filtration? These kernels of the continuation maps. Well, from the point of view of this Morse-Bott spectral sequence, it's basically asking, when do these ordinary cohomology classes get killed in a spectral sequence? So here you see, for example, these two classes, for grading reasons, have to kill those two classes. So that means that at period 1/3, at slope 1/3, just after slope 1/3, those classes are getting killed. So that means that these two classes here live in the lowest filtration value. And then later on, some later column will kill off the unit. And so that means that that unit is separated in our kernels, is separated from the degree 2 classes of ordinary cohomology. So the filtration that we're getting on quantum cohomology is basically asking at what stage do these Morse-Bott manifolds manage to kill the ordinary cohomology via Floer differentials in the spectral sequence. All right. Okay. And the next thing I want to say is also we managed to calculate what these symplectic cohomology groups are. So the symplectic cohomology in this case turns out to be a quotient of quantum cohomology, or if you like, it's a localization of quantum cohomology at a special class. So associated to this Hamiltonian S1 action, there's a rotation class. So for closed symplectic manifolds, this is called the Seidel element, and it's an invertible class. But in this non-compact case, these are non-invertible elements. And it turns out that I'll mention this later in the talk, that the continuation maps turn out to be a repeated application of quantum multiplication by the special class Q on quantum cohomology. And so these give rise, so the symplectic cohomology then is a quotient of quantum cohomology by this E0 space, which is the generalized zero eigenspace of quantum product by Q. But you can also think of it as a way of as a localization of the algebra at this particular element Q. Okay, and I'll give you some explicit examples just so you have give you a flavor of what's going on. So here's an example in the Calabi-Yau case. So by that I just mean that C1 is 0. Symplectic cohomology is always 0. That means that these kernels eventually exhaust all of quantum cohomology. So for large enough slope, we get all of quantum cohomology. And by the long exact sequence, all of these classes can be represented by positive symplectic cohomologies. This was the story that we had also in the Chi correspondence case. Now, if you are in non-Calabi-Yau cases, like Fano cases, the story becomes more complicated. And sometimes not all classes in quantum cohomology die via these continuation maps. So for example, for O of -1, the O of -1 bundle over CPN, so the ordinary cohomology is just the same as the cohomology of CPN, so it's n plus 1 dimensional. But what happens is that these kernels, this E0, becomes one dimensional. So one dimension worth of the quantum cohomology dies, and the symplectic cohomology has dropped by 1 in dimension. And you can also do this for larger slopes. So for O to the -n, the rank will drop by n, and eventually the Calabi-Yau case is when you reach curvature -n-1, and that's exactly when the symplectic cohomology vanishes. So this is the story. So this is all the non-equivariant story, and today I want to talk a little bit about what happens in the equivariant case. So before I can talk about equivariant Floer cohomology, I just want to say a few words about classical S1 equivariant cohomology. So you're probably most familiar with the Borel construction of equivariant cohomology. So that means we're working on we're working on S infinity cross our manifold S1, and we're taking the cohomology of this. So this is one version of equivariant quantum cohomology. Equivariant cohomology. In this case, you get a module over polynomials over U, where U is the equivariant parameter in degree 2 that generates the cohomology of CP infinity. But there are also other versions of equivariant cohomology where, for example, you might want to formally invert U, so localize at U, in which case you get Laurent polynomials in U. Or there's also this other version which has been used a lot in Floer theory where you quotient out all positive powers of U. So this has a slightly different flavor. Instead of U behaving like a polynomial, U behave in a nilpotent way. Sufficient applications of U will eventually give you 0. So these are these three versions, minus, infinity, and plus. And the most familiar one is the Borel one, which is the E minus. Now here you notice from these brackets that I put these double brackets, which means that I've completed in U. So I'm allowing series in U, and I'm actually doing Laurent series in U. Classically, you don't need to do this, but in the Floer theory, you do need to do this because you're counting moduli spaces in Floer theory where arbitrary high powers of U might arise. So that's why I've completed in U. All right. Okay, so let me show you a very simple example of this. So just a classical, just a manifold, the circle with S1, so with the circle acting on itself with weight 1, just by rotating. So we can do the Morse picture of this. So we have a height function with a minimum and a maximum. But you can give this to your PhD students, and this is actually already this very simple banal example is actually quite tricky, because when you do the equivariant theory, you actually have to work on this Borel model. You have two dynamical systems at the same time. You have this dynamical system Morse theory on S infinity, and then on the manifold side you have this parameterized Morse theory. So it's actually quite tricky to do this. In any case, I'll show you what comes out. So these are the three chain complexes you get. So on the left, you see we've got the minimum X, the maximum Y. You've got these powers of U, which come from the coefficients, and these powers of U, they correspond to critical points on the S infinity side. So in the first picture, you see this polynomial behavior in U. In the middle picture, we allow inverses of U. And in the third picture, we've quotiented out by positive powers of U. And I've drawn for you, so each dot corresponds to one copy of the ground field, and the arrows correspond to differential, and they're all isomorphisms. And so you see in the first case, everything cancels out except for the minimum. In the middle picture, everything cancels out. And on the right picture, everything except the maximum cancels out. And so you get three different answers for these three groups. Right, let me now mention, in our setting, we're doing Morse theory for a moment map, and there's this classical work of Kerwin called Equivariant Formality. So what happens if you are studying the Hamiltonian compact Lie group action on a symplectic manifold, the equivariant cohomology looks as if you had a trivial action. So it's just the ordinary cohomology tensored with the equivariant cohomology of a point. So in this case, you're just throwing in whatever polynomials in U, Laurent series in U, or this nilpotent type thing. Okay, so this is just this is a non-canonical isomorphism just of the modules. Okay, and the last classical thing I want to mention to motivate what I'm doing in the Floer theory side is the localization theorem. So this is a classical result of Borel. I'm always working with fields over characteristics 0. So what you can do when you're doing the equivariant theory is you have a natural map where the inclusion of the fixed locus, which on cohomology is you're pulling back from the equivariant cohomology of the closed manifold to the equivariant cohomology of the fixed locus. And the Borel localization theorem says that this becomes an isomorphism after you've localized this equivariant parameter U. And so now remember that we called E infinity the theory where we're localizing U. So another way of stating this is that the E infinity theory, so the middle version, for the compact manifold, it basically only sees the cohomology of the fixed locus up to throwing in these Laurent theories in U. Okay, and let me just quickly show you, if you look up here, why did we get 0 from this point of view? It's because we had an S1 action S1 where rotating, there's no fixed points. So the fixed locus is trivial, And so this vanishing is consistent with the fact that there's no fixed locus, so we get zero cohomology. Here on the left, we get something non-zero. This is before localizing U. And notice that this generator X, however, is torsion, is U torsion. So if I multiply X by U, I get 0. And all this U torsion dies off when you localize. Okay, so again, it's consistent with this localization theorem. All right, great. So the drawings. Okay, so now I'm going to tell you about the Floer version. So in the Floer case, I have to tell you what the S1 action is. Now there's two actions in play. So a lot of papers in Floer theory, there have been several papers in Floer theory about the S1 equivariant theory, and it's usually about the action on loops. If you think of Hamiltonian Floer theory as a version of Morse theory on the free loop space, you have an S1 action that reparameterizes the loops. So here you can reparameterize by weight B times reparameterizing loops. In this case, you don't even need an S1 action on the manifold itself. So there's been papers on S1 equivariant Hamiltonian Floer cohomology, S1 equivariant symplectic cohomology, and they refer to this loop reparameterization. Now we are instead in a situation where we also have an S1 action on the manifold. So we have a C star action on the manifold phi, and we can make this the S1 part of that act with a certain weight A. So what we have is we've got two S1 actions. So we have really an S1 times S1 action. But for reasons which will become clear later, it's strategically best for us to just study one of these mixed action at a time. So I call this a weight AB action if I act on the manifold with the S1 action with weight A and on the loop parameterization with weight B. Okay, to make sure that our theorems are stated in a simple way, I'm going to call AB a free weight if non-constant S1 orbits are never fixed by this mixed action. So our theorems can be stated more generally, but they become cleanest in this case. So let me just explain what's going on here. So imagine we have weight 1, 1. So if our Hamiltonian flow So imagine our S1 flow, our Hamiltonian flow coincides exactly with the S1 action on some hypersurface. So then what's happening is this S1 action is rotating forward by the S1 flow, but at the same time, because we're doing weight 1 in the loop, we're also reparameterizing the loop. So we're going in the opposite direction. And so these two actions can cancel out. And so even though you have a non-constant S1 orbit originally, from the point of view of this mixed action, it's actually a fixed point. So we're basically excluding the situation. And so most values of AB will be free weights. For example, if you only act on the manifold, it's free. If you only act on the loop reparameterization, it's free. If they're rotating in the same direction, it's free. But for example, this 1, 1 is a case where the dynamics becomes more complicated because the two flows can cancel each other out. So for simplicity, for the rest of the talk, I'm assuming that we have a free, this is a free weight, so they don't cancel each other out. And in that case, we get this localization theorem. So it's exactly like in the Borel case. The E infinity version of Floer cohomology doesn't see any of the non-constant orbits. It just sees the constant orbits, which is quantum cohomology. So the E infinity Floer cohomology is the same as the infinity quantum cohomology. And this is the same as the E minus equivariant theory. So the usual Borel model localized at U. Okay, and if we take the direct limit of this, then we get the same for symplectic cohomology. So the E infinity symplectic cohomology is just the E infinity quantum cohomology. Now, with everything we've done so far, this is actually not so difficult to prove. So let's have a look again at our Morse-Bott spectral sequence. This was the picture we had in the A2 singularity case. So we have all these Morse-Bott manifolds of orbits arising as the Hamiltonian grows, but now we're doing the equivariant version. So we're doing equivariant cohomology of these Morse-Bott manifolds on the E1 page. But because we have a free weight action on these Morse-Bott manifolds of non-constant orbits, this action has no fixed point. So the classical Borel localization theorems tells you that the classical equivariant cohomology of these Morse-Bott manifolds has, in the E infinity case, have to be 0 because there's no fixed points. And so that means all of that stuff vanishes, and the only stuff that survives are the critical points of the inside. And that gives us the ordinary cohomology, or if you like, the ordinary quantum cohomology with this extra U parameter thrown in. Okay. And now I should say that the idea of thinking about the localization theorem in the context of Floer theory goes back to this very nice paper by Zhao from 2019. And so she was studying Liouville manifolds, so exact symplectic manifolds. And the S1 action she was looking at was exactly this reparameterization action on loops. So there was no action on the manifold. And the proof is was a bit different from ours. And so in our context, this result arises in this slightly different way. But this is where this whole idea originated. Okay, and now the next thing I want to look at is to talk about the filtration now in this equivariant context. So the E plus theory behaves very much like the non-equivariant theory. So we have these kernels of the continuation maps, these kernels grow, and very often when you do the direct limit, this E plus symplectic homology vanishes, just like the ordinary symplectic homology often vanishes for these manifolds. Now these cohomologies have also U actions, so you actually can make the filtration more interesting by making it a bigraded filtration, where you also consider at what stage the classes get killed by the U action. So it has a bit more information than just the kernels. Now the interesting thing happens actually with the E minus theory, so the usual Borel version, and the E infinity version. And this caught us by surprise, because here we thought also that these kernels would grow in some complicated way. But in reality, the kernels don't grow at all. So what happens is that the continuation maps suddenly all become injective. So that means that these Floer cohomologies are growing more and more and more. And we're getting new and new classes always added to our original cohomology. And this as well, from the work we've done before, is not too difficult to prove now from everything we have. We're going to look at this diagram. So here on the top vertical map is just the continuation map in the E minus theory, and the bottom horizontal map is the continuation map in the infinity story. So now remember the bottom one here we said by the localization theorem is an isomorphism. The infinity quantum cohomology is the same as the infinity Floer cohomology. The left vertical map is the natural map you get from the E minus to the infinity theory. So localization at U. By the equivariant formality theorem we had, the equivariant classical cohomology as a module is just the ordinary cohomology, just with these extra U parameters thrown in. So here on the left, we have an injective map. And so if we go downwards and to the right, we get an injective map. So that means that also the top horizontal map composite is injective, which means the top map, this top continuation map is injective, which is quite surprising. Okay, so let me clear these drawings. Okay, and so now the question is, if these are injective, it means the kernels have no interesting information. Can we still define a filtration? And here, after thinking a little bit about what is a natural filtration that you can define on KU modules in algebra, the natural answer that we came up with is the following. You look at the ordinary cohomology classes, you apply the continuation map, and then you look at those classes which are of order U to the n or higher. So here there's a technical fact that we also have to kill off any U torsion. But once you've killed off the U torsion, we're basically saying this filtration at level n is looking at which classes in the ordinary cohomology, once we map them to the Floer cohomology for that slope, for slope k, whether they become divisible by U to the n. Okay, and here below I've written this in an equivalent way. So we're still looking at the continuation map, but we're sort of killing off anything of order U to the n or higher, and we're killing off the U torsion. So the first time you see this might look a little bit ad hoc, but this is the natural filtration that you would come up with if you thought about KU modules and filtrations on KU modules. And it's also the natural choice if you consider the fact that these equivariant cohomologies, there's a natural long exact sequence from the minus theory to the infinity theory to the plus theory. So this always occurs. So you have this long exact sequence, and this filtration that we defined on the E plus, just the kernels above, this new filtration on E minus, and then a naturally induced filtration we get on E infinity from that. All those filtrations are now get respected by this long exact sequence. So this again shows you that this filtration is a natural choice to use. And here I'll just mention in passing that when we take the direct limit of this, we actually get a short exact sequence respecting filtrations on symplectic cohomology. So you might wonder why I'm keeping track of all these three theories and not just focusing on one. The reason is that in applications, often you can find out information about one of the three theories more easily than the others, and then you use these long exact sequences to tell you, or short exact sequences tell you things about the other equivariant groups that you care about. All right. So the next thing I want to tell you about is that how we can actually calculate equivariant quantum cohomology. So let me just briefly recap. In the non-equivariant case, this is an old paper of mine. I told you that there's this rotation class, which is like a sidal element, and symplectic cohomology is a quotient of quantum cohomology. How does this arise? This arises because these continuation maps where we're increasing the slope, if we look at integer slopes, we keep increasing these slopes. One can actually identify integer, one can actually use this thing called the sidal isomorphism. This is basically just multiplying one orbits by the S1 action. What happens is you get S1 orbits, but of a new Hamiltonian, and the new Hamiltonian is a difference of the old Hamiltonian and the S1 action. So that's why we're getting a drop in the slope by 1. And so we can keep dropping these slopes until we get back to ordinary quantum cohomology using these sidal isomorphisms. And so these continuation maps correspond to just maps from quantum cohomology up to some grading shifts. And it turns out that these are all quantum product by this rotation class Q. That was how the story in the non-equivariant case came about. In the equivariant case, the story is a little bit more complicated because this weight, remember we have this mixed action. Unfortunately, these weights also can keep changing as we apply these sidal isomorphisms. In any case, we have, by the injectivity theorem, we know that in the E- theory, all these continuation maps are injective. So our Floer cohomologies are growing and growing and growing. Now, unfortunately, as they're growing, we keep landing in these different quantum cohomologies for different weights, which is a bit frustrating. So what we would like to do is actually try to compare all of these inside a fixed ambient module. And so here we do a little trick from algebra. So we would like to go back, we would like to somehow go backwards. When you're working with module homomorphism, injective module homomorphisms, there is a map that goes backwards. And it's the thing in linear algebra called the adjugate map. Okay, so the adjugate map allows you to go back. And the inverse map is the inverse map in linear algebra is precisely is this adjugate map divided by the determinant. Now, the division by the determinant is something that makes me typically go outside of my original ring of coefficients, and that makes sense because I'm trying to fit my new classes in a space that came. So here I've already filled up all of these are injectively included, so these are already all filled up. So I need more space to where to put my new classes, and so that's why I have to now allow series in U to injectively bring these classes back. And in any case, intuitively, what's happening is that here we had our original equivariant quantum cohomology, and here in the U to the 0 part is the ordinary quantum cohomology. And what's happening is that we're introducing these new classes coming from the Floer cohomology, and they arise with negative powers of U. And so these blue classes, these new classes, they're a bit like a virus that keeps growing. Sorry about the analogy with viruses after the COVID period, but it's like a virus that's sort of growing, because all the maps are injective, this just keeps growing and growing. And so now we're interested in we're interested in invariants associated to these sort of setups, to these KU modules that keep growing in this way. Okay. So let me give the first non-trivial example of this, the cotangent bundle of CP1. And we're just going to go to slope 1. So we've made the Hamiltonian grow until it becomes the S1 action, or slightly faster than the S1 action. Now, you saw from above that so here in this case, the shift in index, this mu, which is the Maslov index of the S1 action, happens to be 1. So what's happening is the quantum cohomology shifts by 2 in grading. So you might think that what's happening with the quantum cohomology is just that it's shifting down by 2 in grading. And so naively, you might think, okay, I'm just getting my classical quantum, my equivariant quantum cohomology, and then 2 new classes because of the fact that I have now a U inverse. So this would be a a very reasonable expectation that this is what's happening. And actually, interestingly enough, the Floer theory is more complicated. These two new classes can also arise in a different way, without contradicting the grading. So here you see this is the cohomology of CP1. This is the equivariant cohomology CP1, and here are these new classes. But the new classes can also be arranged just on the right column. And you see, you still have the same dimensions in each grading. So from the point of view of grading, everything is correct. But from the point of view of the module structure, notice that here this unit, has not become U divisible in the Floer cohomology for slope 1, whereas some other generator has suddenly become U squared divisible, so more divisible than you might expect. And this is actually the picture that happens. So there's some non-trivial Floer theory that's happening, and so the module is changing in a non-trivial way. And all these pictures, they mean something for the filtration. So let me just explain in the simple example what this means for the filtration. So here, this filtration, remember this bottom index is telling us what slope we're at. So slope 0 means we're just doing classical cohomology. And here, the power on top tells us how divisible we are by U. So this F00, we're looking at just these two classes, the classical quantum cohomology with no powers of U. And here, this intersection, we're asking, when I go to slope 1, so when I've increased my Hamiltonian to go to slope 1, which of those classes have become, and here the two, have become U squared divisible? And here the answer is that we've got to have a one-dimensional space worth of classes that are U squared divisible, because here we have this new generator that under multiplication by U squared, this gives rise to some interesting class in classical quantum cohomology that's U squared divisible suddenly in the Floer theory. Yeah, so all these pictures, they mean complicated things for these filtrations. All right. So let me now tell you a little bit about what's happening now more generally. Oh yeah, so first I want to say something about equivariant formality. So you might ask, do you get equivariant formality also for the Floer theory? So in this case, I'm assuming our manifold is either Calabi-Yau, meaning C1 is 0, or Fano. C1 is a positive multiple of the class of the symplectic form. Now, remember what I told you before, in the classic non-equivariant case, symplectic cohomology is a quotient of quantum cohomology. And there's this E0, which is this generalized zero eigenspace of this rotation class. And here you can do a non-canonical, it's not the most elegant thing, but just for simplicity, you can do a non-canonical isomorphism. The quantum cohomology has a symplectic cohomology part summoned and this E0 summoned. Okay, the theorem we have is that in the Calabi-Yau or the Fano case, for the E plus theory, we do get equivariant formality. The equivariant cohomology is just the ordinary cohomology up to changing the ring by inserting the coefficients that you get from equivariant cohomology of a point. However, in the E minus and the E plus theory, something interesting happens. So here, the symplectic cohomology, the ordinary symplectic cohomology, this E0 part vanished. It got killed. And suddenly this E0 part gets resurrected in the equivariant theory. And that part, even in the E minus theory, actually has Laurent series in U rather than just polynomials in U. So there's the equivariant formality part that you would expect, classical symplectic cohomology, and then polynomials in U, and then this unexpected summand, which is resurrected from the classical cohomology with Laurent series in U. And so below here, I've tried to give you a picture of this. So here you have this. Below you have the symplectic cohomology. Here you have polynomials in U, and then here you have this. On the right you have the E0 part, which lives here. You have the polynomials in U. And what's happening as you increase the slope is that you have these new classes, like this virus that is sort of growing, and it grows more and more and more. And as you increase the slope, you get more and more new classes, and eventually you will get E0 Laurent series in U. Whereas this part here doesn't change as you increase the slope. All right. In the Calabi-Yau case, this is particularly nice. In that case, ordinary symplectic cohomology vanishes. So a lot of these things go away. This vanishes. E plus is 0, and only these E0 parts survive, and the E minus and the infinity theory are the same. Okay, so erase this. Okay, let me give you a concrete example of this. So the two examples we saw earlier, for the cotangent bundle of CP1, the E minus symplectic cohomology has two copies of Laurent series in U, whereas in the O of -1 case, so the blow up of C2 at the origin, we have a polynomial KU part and a Laurent series KU part. And that's because the symplectic homology is non-zero. That becomes this polynomial part. It's one-dimensional, whereas it has a one-dimensional E0 part coming from the kernel of the multiplication by this rotation class Q, and that gives rise to a Laurent series sum and K round brackets U. Okay, and so so now I'll tell you. I want to tell you about invariants that you can get. What sort of invariants can we extract from this filtration by equivariant Floer groups as we increase the slope? So I go back to a very basic example. Our continuation map is actually a map between three KU modules. And so here I'm just saying, let's look at a very basic example. Let's look at a KU module map from rank 3 KU to rank 3 KU, given by this matrix. Now, the fact that we're using just one mixed action at a time means we've got this very nice ring. KU is a principal ideal domain. In fact, it's what's called discrete evaluation ring with parameter U. That means that up to changes of basis on the domain and codomain, our homomorphisms can be diagonalized with different changes of basis on domain and codomain. And on the diagonal, we have these elements which are called invariant factors, and they're just powers of this DVR parameter U. So basically, the module homomorphisms, all of their information up to isomorphism is just encoded by these diagonal elements, which are just powers of U. So it's discrete information. And when we do the inverse of our continuation map, this KU cubed then looks like this. There's one element here because we multiplied by U. When we take the inverse, we've inserted a U inverse. And this U3 creates a U minus 3, and this U to the 4 creates a U to the minus 4. So this is what's happening. Here we've got this new U to the minus 1 class. This is this new U to the minus 3 class, and this is this new U to the minus 4 class. And so these new blue classes that we're getting because these Floer groups are increasing, what they give you is a picture that's called a Young diagram. It's just a combinatorial way of encoding how these one-dimensional summons are growing. And there's two ways of viewing it. You can either view it as saying these boxes tell me which powers of U I have. I have U to the 1, U to the 3, U to the 4. It's a number of boxes. If I look vertically, or if I look horizontally here, I'm basically asking how many of our ordinary quantum cohomology classes become U to the 1 U divisible, or U squared divisible, U3 divisible. These have to do with these slices. And the dimensions of these slices are these numbers 3, 2, 2, 1. This is what you get if you turn this Young diagram around. And so these are the natural discrete invariants that you get from a picture like this. And so what we define is we define this filtration polynomial, which keeps track of these numbers di. Once you know the di's, you can flip the Young diagram and get these ji's, so they tell you the invariant factors. So all the information from the point of view of the KU module homomorphism is all encoded in this filtration polynomial. In our example above, we get this polynomial here. This 3 is the dimension of this slice here, the ordinary cohomology. This 3 is this next slice, and then 2 and 2 are the next two slices. And then this last coefficient 1 is because of this class here at the bottom. So this filtration polynomial is encoding all the interesting algebra information as a KU module for these KU module homomorphisms. Okay, and let me remove the annotations. Okay, and so here's our example from before, T star CP1. We had the naive case where we just said, okay, imagine that quantum cohomology just gets these two extra classes. That would correspond to a matrix of the form U00U. So we would get invariant factors U and U. And so here the filtration polynomial would be, you would get a 2 and a 2 because of the dimensions here, 2 and 2 dimensions. On the other hand, what actually happens for T star CP1 is you get this interesting map, which is one of the class, you get one class which suddenly becomes U squared divisible, but the unit does not become more U divisible. So you have invariant factors 1 and U squared. And so here the slice dimensions here, 2, 1, and 1 become these coefficients of the filtration polynomial. So again, you see the filtration polynomial is just encoding all of this discrete invariants packaged up in a nice way. All right, let me erase this. And so now let me tell you the general story. So the general story is, remember, we have these, we start off with the E minus equivariant cohomologies, the Borel version of equivariant cohomology. We have these continuation maps that give us the E minus Floer cohomologies for these slopes HK. And then we're using the continuation map to map this back to original quantum cohomology, but allowing now negative powers of U so that we have enough space for this sort of virus of blue classes to increase. And as we increase the slope, for each slope value, we get a Young diagram. And what we're getting is these nested Young diagrams. And to each of these Young diagrams, we associate a filtration polynomial. And so we have these sort of increasing filtration polynomials with these discrete invariants DJ that tell us everything. They tell us everything about the continuation maps up to isomorphism. They tell us the invariant factors and so on. Now, everything I told you before is the sort of messy stuff that an undergraduate would do, choosing a basis and so on. So it all looks like you're getting invariants, but you've made some very clever choices of basis to present the module in a certain way. And it's not so clear how invariant the whole thing is. But it turns out that these very naive invariants DJ that we got, which are the slice dimensions, so how many new blue classes you're getting for U to the -1, U to the -2, and so on, these are precisely measuring the dimensions of these quotients of the filtration. So let me remind you again what these filtrations mean. So the K is just telling you which slope we're looking at. So this is a Hamiltonian that an infinity is K times the moment map. And the top value here is telling us it's UJ divisible. So these are the classes in ordinary cohomology, ordinary quantum cohomology, that when you map them to Floer theory for slope K, they become U to the J divisible. Now, if you think of these filtrations as increasing, and you imagine for a moment that you pretend that this one here, the U to the J -1 divisible classes, are something that we previously understood inductively, then there's some obvious U to the J divisible classes you know. If you had a class that was U to the J -1 divisible, and you multiply it by U, it becomes U to the J divisible. So this Fj contains very naturally U times Fj -1. And if you think about filtrations of Ku modules, you see these filtrations, they're all infinite dimensional vector spaces over K. So there are no interesting invariants like dimension. But if you consider this inclusion here, this is like, if you take the quotient of these two, so you're killing off the classes that you obviously expected were going to be UJ divisible, suddenly you get finite dimensional invariants. So we prove that these are finite dimensional invariants, and they are exactly the invariants that we got from the previous picture, where we explicitly chose a basis for the module and so on. So these are the natural invariants that you would associate to a filtration of Ku modules. All right, and now in addition to this, so these are invariants of the equivariant quantum cohomology. You actually also get invariants of the classical quantum cohomology, the non-equivariant one. So the way you do this is if you kill off anything that's a multiple of U in the quantum cohomology, equivariant quantum cohomology, that just gives you ordinary quantum cohomology. That's like setting the equivariant parameter U to 0. And it turns out that these quotients that we studied here, they filter the ordinary cohomology, or if you like, the ordinary quantum cohomology. So we're getting a non-linear. So this is in this context in algebra. You talk about a Hilbert-Poincaré series. If you have a filtration like this, you look at the successive quotients. You can get if you like, you can write down a non-canonical isomorphism of your vector space in terms of these successive quotients. And the Hilbert-Poincaré series is just a formal series with this formal variable t, where the coefficients are telling you the dimensions of these summands. So it's telling you basically the dimensions of how you're filtering. And so what we're getting is this Hilbert-Poincaré series, and we're getting the dimensions of these successive quotients. They're the differences of these interesting D parameters, the dimensions of the U to the -J slices. And these dimensions are exactly the number of invariant factors of the particular power U to the J. And conversely, from the Hilbert-Poincaré series, you can reconstruct the filtration polynomial recursively. So these two polynomials, the one that we call filtration polynomial and the one that we call Hilbert-Poincaré series, they're equivalent to each other. You can recover one from the other. So in the first case, they're encoding invariants of the equivariant quantum cohomology, whereas the second one, the Hilbert-Poincare series, is encoding invariants of the classical cohomology, but the way you got these invariants depended on the equivariant Floer theory. That's how you got the filtration, these quotients, and so on. Okay, so this is all good, nice and good, but in Floer theory, usually one can't calculate anything. But it turns out that here we can actually calculate a few of these things, and we're currently thinking about other classes of examples, especially toric examples. But here's a list of three examples we talked about previously. If the manifold is just C, for example, this is the filtration polynomial is this. So what that means is that you have your original quantum cohomology, then you have the various powers of U, and the new blue classes, they are just growing linearly. So for slope K, you get exactly K of these new blue classes, and the Hilbert-Poincare series that we're getting is just T to the K, and that's telling us that the continuation map. This is basically telling us the continuation map is a 1-by-1 matrix with just one invariant factor, which is U to the K. So these polynomials are encoding everything you might care about up to isomorphism of the continuation map. For O of -1, so the blow-up of C2 at the origin, you get this filtration polynomial, and this is the series. So here, let me just remind you, this is the Fano case. So we had a piece which was the symplectic cohomology, and then with polynomials in U. So we have these classes, and that part, as we increase the slope, was not changing. Whereas there was the U0 part, the E0 part, where I told you that these guys, that's where all the new classes start to grow. And so the matrix that we're getting in this case is 1, 0, 0, U to the K, and so this T to the K is telling you about this. Where are we? Here we are. This is telling you about this U to the K power, and this 1 is telling you that you have a 1 here. So again, it's encoding the continuation map for slope K. And then in the T star CP1, that already becomes tricky. So we're currently trying to figure out precisely what it is, but it's one of these two cases. So you either have this polynomial with these final two terms, or it might be these two final two terms. So when for slope 0, you get this thing on the right. For slope 1, you get this one. And then we know, for example, that if this one ever arises again, then immediately afterwards, this one must arise. But for all we know, there might be a lot of back and forth switching. So we're currently trying to just be, we're hoping to be able to say, I don't know, maybe that this happens for all large values of K or something like that. But anyway, so already the T star CP1 case is a little bit tricky because, in general, we can't really ever calculate explicitly these Floer maps. There's usually some indirect argument. Okay, so oops, I'm already slightly out of time. I think, was this the last? Oh yeah, so this was the last slide. So here I just drew for you the last picture, which shows you that this T star CP1 case, how it's non-trivial. Here you see the cohomology of CP1. Here you see the cohomology of CP. Oops, here you see the cohomology of CP1. Yeah, so two-dimensional, and you see the blue classes growing. And two situations could happen. We could have this naive inclusion where the quantum cohomology has just been shifted down by 3 classes, or you could have this more interesting situation where, where some classes in quantum cohomology become U² divisible, some become U to the 4 divisible, so more than you might expect, not U³ but U4, and that gives rise to these two types of filtration polynomials. And so there's these two types of continuation maps. It could either be a U² U4 continuation map for the slope 3 case, or it could be a U³ continuation map. And so yeah, so now we're thinking about the toric examples, whether we can say more precisely what these polynomials are in the toric case, semi-projective toric varieties. Okay, I'll stop here. Yeah.
Okay. Thank you very much. Maybe we have some questions. So
maybe I have a little bit vague question. So at least on closed manifolds, so we had with Dickstein, Ganor, and Zapolsky the notion of ideal valued measure, which is like kernel from the map from quantum cohomology to symplectic homology a la Varalgunas of the complement. And you get some ideal. And my question is the following. So can you associate with the ideals with which you get in, at least in usual quantum cohomology, some subsets or some geometrization of your algebraic picture? So does it exist or not?
So you're saying whether these kernels of quantum cohomology, whether they're telling you something geometrical?
Yeah, so whether you have, for instance, a filtration of whether you can correspond to subsets of your manifolds, these ideals in quantum cohomology.
Subsets.
Yeah, but maybe reverse engineering. So you already have this ideal. So maybe you can just indicate that these are interesting sets which correspond.
All right, I see what you're saying. Right. Yeah. So. Yeah. So. Yeah. So Mike. Yeah. So. Yeah. So my guess would be. Yeah. So I haven't tried doing a version of relative symplectic homology. That would probably be the right approach to this. But from the point of view of just from the point of view of algebraic topology, we have this. We have this map from positive Hamiltonian Floer cohomology to the classical cohomology. And so what we're counting is, let me see if I can go back. How do I go back? Lots of slides. Maybe I can draw it here. Yeah. So we had this picture at the beginning where we're counting these sort of Floer disks, and here, if you can look at the moduli space of these Floer disks from the continuation map, and then instead of using a Morse model on the inside, you can instead use just a marked point and evaluate, and then you would sweep some pseudo cycle on the inside. And so this would correspond to the cycles, the classical cycles that are getting killed. So basically, this is the kernel that we care about. So this kernel is represented, if you like, geometrically by these unions of these pseudo cycles that you're getting from this map from HF plus of HK. So we have this map from ordinary cohomology to there, and under evaluation you're getting these cycles, and these pseudo cycles, they are in the kernel of this map, C star K. So I don't know exactly which natural geometric subspace to associate, but it would probably be some geometric subspace that's like a fattening of these cycles, because that's where all the cohomology is supported. So that would be my guess.
I see. Thank you very much. Interesting.
The other thing maybe that's worth saying is that in our first paper we also these sort of spaces have been studied in the algebraic geometry world by Tamás Hausel and other authors, and you have this picture which is a bit similar to what we had for Liouville manifolds. We have this R plus flow, which is like the analog of the Liouville flow, sort of for Liouville manifolds. But this is part of the C star action, and this pushes the whole manifold into an area called the core. So you have this, and this is usually a singular thing, just like in the case of that we know from Liouville manifolds. And in this core in particular, you have the fixed locus. Yeah, though that's smooth, but the core is typically singular. So once you know what sort of cycles you're hitting, what you can do is what the algebraic geometers do. They create cycles by looking at for example, the downward flow. These give you they call these the downward cells or upward cells. And so the downward cells that are hit by these Floer trajectories, they would give you so not a smooth step manifold, but they would give you they would give you in the algebraic world, they would give you like a typically a singular subvariety. And so that again would be a natural candidate for a way of representing this kernel. Yeah.
Maybe there are some other questions.